All right, let's talk about one of the very first sorting algorithms that most people in computer science ever learn. It's called bubble sort. And you know what? It's simple, it's super intuitive, and its name, well, its name tells you pretty much everything you need to know about how it works. So let's dive right in. So let me ask you something. If I gave you a totally jumbled list of numbers, how would you go about sorting it? I mean, what's the simplest set of instructions you could come up with to get them in perfect order every single time? Well, that's the whole point of a sorting algorithm, and we're about to break down one of the absolute classics. Okay, first things first. What even is bubble sort? Let's take a closer look at this so-called bubbly algorithm. At its heart, the logic is just incredibly simple. Really, the algorithm just steps through a list over and over again, and it only ever looks at two numbers at a time, the ones right next to each other. If those two neighbors are in the wrong order, it just swaps them. That's literally it. It just keeps doing that until there are no more swaps to be made and the whole list is sorted. And that is where it gets its awesome name. Just picture it. Think of the biggest numbers in the list as bubbles in a fizzy drink. What do? They naturally rise to the top, right? Well, that's exactly what happens here. With every single pass the algorithm makes, the next biggest number bubbles its way up to its correct spot. Okay, Siri is one thing, but seeing it in action is way better. So let's do a step-by-step walkthrough and watch how this actually works. All right, here's our starting lineup, a messy little list of 5 numbers. Our goal, our mission, is to get these guys sorted from smallest to largest using only the rules of bubble sort. Okay, first pass, step 1. The algorithm looks at the very first pair, 6 and 2. Is 6 bigger than 2? Yep, so they're in the wrong order. What do? We swap them. Boom, the list is now 2, 6, 11, 7, 5. See? Simple as that. All right, moving on. The next pair is 6 and 11. Are they in the right order? Yep, 6 is smaller than 11, so we leave them alone. But then we get to the next pair, 11 and 7. Aha! 11 is definitely bigger than 7, so they get swapped. You can already start to see it, can't you? Those bigger numbers are starting to drift or bubble towards the right side of the list. And for the last step in this first pass, we look at the new pair, which is now 11 and 5. Another obvious swap. And just like that, our first full pass through the list is done. And here's the cool part. Take a look. The biggest number in the whole list, 11, has already bubbled all the way to the very end. It's now in its final correct position. It's sorted. So if you boil it all down, you get this super simple recipe. You start at the beginning, you compare two neighbors, you swap them if you need to, you move one step to the right, and you just repeat. You keep doing that until the whole job is done. That's the fundamental loop, the DNA of bubble sort. Okay, so we've seen it work with our eyes. Now let's get a little more formal and look at how we'd actually write this down as a recipe for a computer. The real engine driving bubble sort is something called nested loops. It's just a fancy way of saying you've got a loop running inside of another loop. You can think of it like this. There's an outer loop that's kind of the manager, deciding how many big passes we need to do. And then there's an inner loop that's the worker, doing all the heavy lifting of comparing and swapping on each of those passes. Yeah, so that outer loop is the boss. Its only job is to make sure we keep running the process enough times to sort everything. You saw how after one pass, the biggest number was sorted, right? Well, after the second pass, the second biggest number will be sorted. And after the third pass, well, you get the idea. The outer loop makes sure this continues until the list is perfect. And if the outer loop is the boss, the inner loop is the hard worker. This is where all the action happens. For every single pass the boss orders, this inner loop is the one that actually marches down the list, one pair at a time, doing all that comparing and swapping that we just watched happen. But hang on a second. What if the list is already sorted from the get-go? Or it gets sorted early? Our basic recipe would just keep on making pointless passes, wasting time. So we can add a clever little trick. We use something called a swapped flag. The idea is simple. If the inner loop makes it all the way through the list without making a single swap, what does that tell us? It tells us the list is already sorted. And that flag is our signal to just stop everything early. It's a really simple but super effective optimization. Okay, so now we know exactly how it works. But that leads to the million-dollar question, is it actually any good? I mean, is it fast? To answer that, we need to talk about its performance. And that brings us to this great analogy of fast rabbits and slow turtles. So this table tells the whole story using something called Big O notation, which is just a way to talk about how efficient an algorithm is.
Now, in the absolute best case, let's say the list is already sorted when we start. It's pretty quick. We call that O of n, which means the time it takes grows in a straight line with the number of items. But, and this is a big but, in the average case, and especially in the worst case, it's O(n squared, or n squared. And that, my friends, is bad news. It means if you double the number of items you're sorting, the time it takes could quadruple. It gets slow really, really fast. The one silver lining is its space complexity. It's O of 1, which basically means it doesn't need a bunch of extra memory to work. It's very efficient in that one way. And to really understand why it's so slow, let's go back to those rabbits and turtles. Think about it. Big numbers, the rabbits, they're fast. They bubble up and zip right to the end of the list where they belong, sometimes in a single pass. But what about a really small number that starts at the very end of the list? That's a turtle. And it is painfully slow. It can only move one single spot to the left with each full pass. So if it's 100 spots away from where it should be, it's going to take 100 passes just to get that one little number home. That is the algorithm's biggest, most glaring weakness.
So that brings up a pretty obvious question, right? If it's this inefficient, why on earth is it one of the first things taught in basically every single computer science course? Why are we even spending time on it now?
The answer is pretty simple. Its real value isn't in its speed. It's in its ability to teach. It's so straightforward that it's the perfect gateway to understanding how algorithms think. It's a fantastic tool for introducing core ideas like loops and comparisons, and this whole idea of complexity we just talked about. Plus, it has a couple of other nice properties. It's an in-place sort, which we mentioned means it's light on memory. And it's also stable, a cool feature meaning if you have two items with the same value, it won't mess up their original order. It's these fundamental building blocks that make it so important to learn first.
And that really brings us to the final verdict on bubble sort. And for this, you don't have to take my word for it. In a now famous interview, the CEO of Google actually asked President Barack Obama what the best way to sort 1 million integers would be. And his answer? He basically said, well, I don't think bubble sort would be the right way to go. Even the president knew its reputation. For a really big job, it's just not the right tool. So that leaves us with one final and really important question. We've established that bubble sort is this essential first step, right? It's the perfect starting point for understanding algorithms, but it is absolutely not the final destination. So if bubble sort is the wrong way to go for the big, tough problems, then what are the right ways? While exploring awesome algorithms like merge sort or quick sort, that's the next step on this whole journey. Thanks for joining me.